Right. Hi. Good morning or good afternoon, everyone. Thank you so much for joining me today for this webinar. And we're just about at 10 o'clock, so I think we're going to get started. So today we are going to be talking about bridging the gap between AI standards and safe AI. So my name is Molly O'Brien. I have a PhD in computer science from Johns Hopkins University. I have expertise and research experience in computer vision, deep learning, and surgical robotics. I work as a senior safety engineer at Exida, and I'm one of our subject matter experts in safe machine learning research efforts and projects. I work on hardware and software functional safety assessments, FMEAs and FMEDAs, and I do a good amount of work in the automotive, process, and semiconductor industries. So today we're talking about machine learning and AI in safety critical tasks. But I think before we get too deep, a good question to ask is, you know, why are we even using machine learning in safety critical tasks? Um, there's it's newer, complex technology, and I think in general, if you're able to solve a problem without machine learning using some traditional approaches, that's generally going to be a good approach to use for now. But what we found is that there are some problems that traditional approaches can't solve. And so, here I'm calling them out in two kind of broad classes. So approaches where you can't specify the task explicitly in all settings. So perception problems are a great example of this. If you were to try and write down on paper, a description or rules to detect every pedestrian in every setting, that's not really something that we've been able to do. And so we found that really the only approaches that have gotten, let's say, a useful level of performance have been approaches that use machine learning. Then there are also some problems where you can't find a parameterized solution, and some complex control problems fall into this category. So these types of problems where you can't solve it without machine learning, that's really the area where we would recommend that is going to be a good place to use machine learning. Oh, and sorry, okay, great. And so people are seeing in the industry that there's this increase of interest in using machine learning in safety critical tasks. And so there have been recent works both out of the ISO 26262 and 61508 committees to provide guidance on safe machine learning. And so recently we've seen two publications, ISO ICTR 5469 and also ISO PAS 8800. And so this guidance, it outlines key steps in a machine learning or AI process. They do a good job of outlining key challenges and risk factors associated with machine learning or AI. And they also give pointers to relevant research. But one thing that's not yet been specified and honestly isn't really agreed upon yet in the industry is how to address the risks of using machine learning when you're designing, developing, and validating ML and safety critical tasks. So here's an illustration of a typical use case when we're using machine learning in a safety critical task. There's some operational design domain or some operating domain. We're going to capture data from real world scenarios, use that data to train a machine learning model, and then we're going to use that model inside of our operating domain. But there's a couple challenges that come along with this. First of all, when we capture data, we're not able to capture the full complexity of our operating domain. This could be because, we can't measure every variable that might be of interest. This is because we can only capture a finite amount of data, and it's not necessarily practical to try and record every situation of interest. Then even on the data that we've captured for training and testing, For any problem with, let's say, a reasonable level of complexity, you're going to still have imperfect performance. So, there are going to be some scenarios where the model doesn't do exactly what you were hoping it would. And then even after we've tested the model, we'll have some measure of, let's say, the average performance. It doesn't provide a guarantee of exactly how well the model will work when you use it in operation. So these are just three of the challenges that anyone would face with trying to use machine learning in a safety critical task. And so today we're going to talk about three approaches or techniques that can at least help address these challenges. And so we're going to talk about semantic data specification, actionable statistical analysis, and online performance monitoring. So first, we're going to take a look at semantic data specification. Now, before we get too deep, I want to spend a minute just talking about data for complex problems. And as an example here, I'm taking a perception problem for, let's say, an automated driving task. So you've got images coming in and some machine learning model, probably a neural network, processing the data, and then the output is going to be some predictions. And so the model, what it's seeing is the pixel information of each image. And so here, just to kind of think about, I've got a reference photo of a red car in, a wooded area, green background. Now, below, I've got this illustration of two dimensions, the pixel content and the semantic content. And when I say semantic content, I'm talking about, the key meaning, relationship, information in the data that we want the model to be able to extract. So here in this illustration below, we've got 4 pictures. We've got another red car in a wooded area. So this is something where you could say, the pixel content may be similar and the semantic content is also similar. But then above we have this red ladybug on a green leaf, red focal area with a green background. In some sense, the pixel content may be similar, but the semantic content or the information in the image is very different. Whereas in contrast, if you think of a blue truck in a desert, the pixel content is very different, but the semantic content is similar to our reference photo. So this is just to get you thinking about when we've got these complex problems with high dimensional data, there's a large space of the possible data that you might run into. And so, how are we going to model this data in a way that's both meaningful, but also helpful to us, as we're trying to solve some engineering problem? And so if we think about specifying the ML model functionality, on the one hand, we have the desired functionality. This is like the requirements we're used to writing down, what the model should do, what it shouldn't do. Then there's the data. And then lastly, we've got some high complexity machine learning model. And for machine learning models, particularly in supervised learning tasks, and this is where you've got a set of data and the desired output you want the model to give you, and during training, you're hoping to train or tune the model so that for given inputs, it gives you the output you would like. And so how the model makes predictions is defined by weights or parameters inside. These weights, you could easily have a model with 1 million weights, which is really just a bunch of matrices of numbers. You can't read the numbers to interpret the performance. And so the question is, when we're collecting data, how can we collect data that both helps us train the models to have the desired performance, but then also we'll have the data that will help us verify the performance after training. And so, I mentioned this idea of semantic data specification. And that's, I'll kind of explain what I mean by that now. So first, imagine we have some functional requirements. This is going to be very, the same as we do with traditional design projects. It's some requirement for what you want the software to perform. So let's say, again, if we're in a pedestrian detection example for some kind of autonomous vehicle, a requirement could be, the perception model should detect pedestrians that are within 1 to 10 meters of the vehicle. Okay, great. So, we've talked about we want pedestrians, but then, for a given task, you can think about maybe what are different semantic groups under the idea of a pedestrian that I want to make sure my model can detect. So I want to detect pedestrians in different poses or with different physical appearances, with different types of clothing. And so you can imagine that if you collect your data and then link both training and testing samples to the different semantic contexts they represent, it at least gives you a way to know, A, I've at least shown my model training samples that cover these different groups that I want to make sure I'm meeting my functional requirements for. But then you can also, in testing, check and see the performance across these different semantic groups and make sure that at least for the parameters that you outlined, you are able, let's say, to detect pedestrians of different poses. And for machine learning models, the data is really the interface between the functionality that you want and the model behavior. So, I think it's logical that this sort of linking of the data to the specification is a way that's tractable and can help you, monitor that the model is learning the performance or meeting the requirements you've defined. And so, during training, the pixel information in this training data that you've linked is going to optimize the model for the functional requirements that you're looking for. Now, whenever we're talking about data, a very logical next question would be, okay, well, how much data is enough? This is a challenging question to really try and give a definitive answer to. Like I mentioned previously, you would want to be sure to have training and testing data that's covering these different semantic groups of interest. I think the exact amount of data you would need is going to depend on your desired SIL, safety integrity level, if you're interested in IEC 61508, or ASIL, automotive safety integrity level, if you're interested in automotive applications, and then also problems that are more complex or have more complex environments would need more data. And I'll also say that even just thinking in this way of linking your requirements to the data, it can help set you up for proactive data collection so that after you've trained the model and you get to your verification steps, you at least have data that's spanning these groups of interest to try and confirm that you've fulfilled the requirements you're interested in. Okay, so we've talked a bit about semantic data specification. Let's talk about actionable statistical analysis. So machine learning statistical analysis is a quantitative analysis used to estimate the model's performance. The output of this statistical analysis, it could be a probability of a correct prediction. It could be something like a failure rate of the model. For machine learning models, since you can't inspect the learned model because it's usually just a set of matrices of numbers that are connected in some way, you really need to do statistical analysis to ensure that the model's learned performance, that it actually learned to perform the function that it needs to do. There's not typically ways of inspecting the model to confirm that it's learned the correct performance. And so when you're doing statistical analysis, you should compare it to some performance target that's been defined for your specific task. That will tell you, the level of performance needed. So, we're used to work with hardware with different failure rate targets for different SILs or ASILs. This would be analogous to that. Now, there are many possible techniques you could use for statistical analysis. People use Bayesian nets, which we'll talk about a little bit more, network generalization prediction. People also use principal component analysis. And so right now, there isn't necessarily one specific statistical analysis technique that you have to use or that the standards would recommend that you use. We would just say as exida, when you're considering different statistical analysis techniques, to pick a technique that can provide insight into what's impacting the model's performance, that lets you leverage your application knowledge, that can help you target if there's maybe certain areas of data that maybe you need more data from, and also help you understand when and where it's safe to use the model. So I'm going to talk in a little bit more detail about Bayesian nets and network generalization prediction. So Bayesian net analysis is a technique where you identify a number of factors that you suspect will impact your model's performance, and then through iterative sampling, observe, the overall performance and can get insight into both the nominal performance, and this relates to, how well, let's say, the model is performing the task, and if you're violating a safety goal or if you're entering a dangerous condition. Something that's very helpful about Bayesian net analysis is if there are known distribution for these factors, you can leverage that and actually, instead of having to have necessarily vast amounts of data or just recording data and having the data kind of reflect these different factors, you can directly leverage if you know these distributions. So that's a little opaque, but here's an example of a Bayesian net that could be useful for an automated driving system. So you may think that the weather, precipitation is going to be important in this control algorithm. So you can sample from, let's say, known weather patterns. Then once you have that, you can model how that's going to impact the road friction, and then model how your algorithm is performing, in the context of a higher level task. Now, if you have another machine learning model, you may not know ahead of time what factors are going to impact the performance. And so this question is actually going to lead us into the other statistical analysis technique that I mentioned. And so this, I will give a disclaimer, this topic is very near and dear to my heart. This is really the topic of my PhD thesis. So if you ever want to talk about it, I'll be happy to talk ad nauseum about this idea. So anyway, so network generalization prediction. This is a technique where you test a model once and then essentially identify what factors impact the model's performance. And once you've done that, essentially leverage patterns to be able to predict how well that model is going to work in other operating domains. And so we're going to talk in a little bit more detail about, how this works. Here for illustration, I'm showing an operating space where we've identified two dimensions that we think are going to be important to the model's performance: the time of day and the weather. This operating space, it's shown as a grid, and one square in this grid is meant to represent a specific context. So here, this X is showing something in partly cloudy weather, between day and night. So, let's say it's late afternoon. That's what this specific context is meant to represent. So the first step is going to be testing the model throughout your intended operating space. Um, Here, the test results are showing green for working as intended, yellow for a safe failure, and red for a dangerous failure. After you've tested, then you want to identify patterns in the performance. And so really, you want to look at each of these contexts and describe the model performance. So, this could be, again, the probability that you had a failure. This could be, let's say the maximum failure rate you observed. You can use different techniques to kind of model this. Then once you've done that testing, you can leverage a probability distribution for a different operating context. And so this is again, a little opaque. Let me give an example. I live in Pennsylvania, where we've got a cloudy day right now, So if I had some, machine learning model and I wanted to test it in Pennsylvania, there'd be, let's say 40% of the time it's sunny, 20% of the time it's rainy, and 20% of the time it's snowy. And so that's my probability distribution, and then maybe there's other weather patterns for the other percentage of the time. If I was going, so I would test throughout that space. Then if I was going to take my car to my friend in Arizona, maybe it's sunny 90% of the time. So I can essentially reweight the test that I've already done on the sunny days in Pennsylvania to get the new average performance if I was going to use a car in Arizona. So that's essentially the idea of this network generalization prediction. Now, you might be thinking, okay, that's great, but I thought we talked about we're only using machine learning for complex problems that we can't solve with traditional methods. And that picture looked nice with those 2 dimensions, but in practice, these problems we're trying to solve with machine learning are very complex. There are many factors that might impact the model's performance, and we don't even know ahead of time which factors are going to be important. And I would say that's a great point. I'm glad you raised that. And I absolutely agree. So to make something like this practical, you have to have a way to, from a large set of possible factors that you might want to model as impacting performance, to narrow down to actually which factors you've observed do impact your model's performance. And so we've done some research on this topic. We have an algorithm based on a measure called the mutual information that we've proposed. It can be a way to rank, if you've got a set of possible factors that may impact your model's performance, which impact it the most. But there's also, other techniques in the literature that you can use to do this type of ranking. And so I'll also mention that this idea of, based on testing, ranking what impacts the model's performance, in this context, I'm talking about it to make this statistical analysis technique practical, but it's also helpful just in general. So seeing from a set of possible factors what impacts the model's performance can be helpful to figure out maybe if you need more data because the model doesn't perform well in a certain context, or maybe I need to have some more test cases in this area because the performance is sort of ambiguous. I'll give one short anecdote. When I was in grad school, I used this network generalization prediction technique on a melanoma classifier, and we trained the model, and then we had these different image statistics, and we looked to see what impacts the model's performance the most, and it turned out to be image saturation, which didn't make sense. That shouldn't be a factor that actually impacts the model's performance, but it turned out there was a false correlation between image saturation and the melanoma diagnosis in our um, oh, in sorry, I'm having a headphones issues. Um, but we found that the there was a false correlation in the data set, and so we were actually able an issue in our training data set because of this type of analysis. So just to say in general, these types of techniques are helpful just in the training and you know collecting and doing sanity checking of your trained models. So okay, great. We've talked a bit about network generalization prediction. Um, from this type of quantitative analysis, you can validate where the model's performance is sufficient. So here in this example, we're showing, in until maybe, let's say, the afternoon, up until partly cloudy, this specific model is working well. This lets you safely use a machine learning model when in appropriate context without requiring the model to be perfect everywhere. So we think that can be very helpful, especially for something like machine learning, where it's very challenging, if not impossible, to try and train a model that really will work very well in all contexts. And kind of one last note on this topic of statistical analysis, we talked about two different techniques, but you can actually use these together. So you could imagine using network generalization prediction for, let's say, a perception model in your system to figure out what impacts the model and be able to summarize the performance. But then if you've got this as part of a larger system, a Bayesian net approach could be a great way to model a complex system and to be able to see how all of these different factors impact your overall system performance. Okay, so on to our last section, online performance monitoring. So this is where we've trained our model, we've tested our model, and now we're looking to use it in a specific operating domain. Now, I'll say hazard and risk analysis. This is, a very classic technique used in functional safety, which gives you a systematic approach to identify hazards and different risks, and it lets you see the severity of the risk and the hazard, and you could use AHARA for a specific model being used in a specific operating domain to identify if it's high or low risk for that application. And if you find that you're using a machine learning model in a high risk situation, another very classic technique would be to use layers of protection analysis. So instead of the machine learning model on its own, it has to be perfect, different layers or diagnostics or alarms that safeguard overall so that the system, has a safe level of performance. And safety functions are something that's very commonly used as a layer of protection. And so safety functions, this again is a technique we're very familiar with in the functional safety industry. And it's a system that will, if a hazard is detected, step in and kind of mitigate that hazardous situation. And now you may be wondering, okay, we're used to pressure relief valves, we're used to this in sort of more traditional applications. What would a safety function for a machine learning model look like? So one example could be a handoff between an automated model and, let's say, a human driver. If you detect you're entering a specific context where you know that the machine learning model does not perform well. Or maybe in different weather conditions, a lower maximum speed that the automated vehicle is allowed to travel at. So again, these types of statistical analysis approaches that give you insight into when the model performs well and when the performance is not sufficient, they allow you to design additional things like these safety functions to achieve a safe overall system. And so, naturally, when you're integrating a trained model into a larger system, you would have to do machine learning verification to ensure that, whoever is using the model, they're following the intended specifications, and that your system overall, the performance is sufficient for your application. And this will also give you insight if you need to design additional layers of protection in this specific system. So if we come back to this operating space illustration, we saw in our previous example that maybe we have a machine learning model that's been validated in these contexts in white, but it has not been validated in these contexts in gray. And this specific user is interested in the operational context shown in red. And so what you would want to do in an application like this is, in the validated context, the model's been shown to be safe, but then identify additional safety functions for these unvalidated contexts. Now, something else that I think is an important piece of this puzzle for achieving a safe overall system is machine learning continuous monitoring. So when we're training machine learning models, again, especially for a supervised model, you've got a set of training data and labels. And so because the data is labeled, you can know exactly whether a prediction is correct or incorrect. But once you start using the machine learning model in operation, there's no labels. You're taking pictures of the road as you're driving, or you're taking pictures of, let's say, a factory floor where you've got an autonomous robot operating. And so you can't rely on knowing exactly whether the model's prediction is correct or incorrect, but there are a number of research areas that can still be helpful. So one thing you can look at is whether the data, as it's getting processed by the machine learning model, is essentially being processed similar to the data you saw in training. And so this relates to seeing how the data gets multiplied through those layers of matrices of weights that I kind of referred to earlier in the presentation. And so there's, a number of research out there looking at what are called the machine learning, the neural network embedding space, or you'll also see the term manifolds used. So that is an area of research that can be helpful. There's also research in what's called error prediction. So this is really just having the model for incoming data predict whether it thinks it's going to be correct or incorrect. And there's also a related field that will have the model predict whether incoming data is in or out of the distribution or in the domain it saw during training. And so then essentially, if something is detected as out of domain, it's an indicator that the model's not going to be sure because this data is quite different from what it's seen during the training process. And so related to that is the concept of data set drift. And so this is saying for even an application that, let's say it's the same year over year, over time, the surroundings or the distributions of the data may shift so that the model that initially was very well trained for this application maybe now is not so well trained. And so this is almost like a silly example, but I think it's illustrative. For many years, skinny jeans were the style. That was the style. And so everybody walking around was wearing, not everybody, but a lot of people walking around were wearing skinny jeans, where now in the last couple years, baggy legged jeans are coming back. And so if you think about from a neural networks perspective, trying to detect people walking around, the shape of people might look different than it did a couple of years ago just because of changing styles. So the concept of data set drift is to be able to detect over time if data starts looking different on average from the training data, before there is, let's say, an incorrect prediction. So I mentioned these topics just to kind of point to different areas of research that can be helpful for designing, let's say, an overall safe system in operation. Okay, so we have talked about 3 topics to help address some risks that there are in using machine learning in safety critical tasks. We talked about semantic data specification, actionable statistical analysis, and online performance monitoring. I'll mention that Exida offers machine learning services. So we have advisory services that help guide the machine learning design and development, analysis services to analyze the model and its performance. So this would cover the statistical analysis that we talked about today, as well as integration services, which verify the machine learning model in an integrated system. So this would relate to the, let's say, machine learning safety functions and continuous monitoring that we just spoke about. I will also say that exida is offering a machine learning course this spring. So we expect to have this listed in May in 2025, and the exact dates will be posted on our website very shortly. We will cover machine learning in safety critical applications, and there will be a combination of both theoretical, like training sessions, as well as some practical coding sessions. So with that, I will say thank you so much to everybody for your attention. We have time to answer some questions, and I'll also say that if there are any questions that I don't have a chance to get to in the session live, I promise I'll follow up over email and we'll make sure that you get the answers that you're looking for. So thank you so much for your attention, and I will take a moment and see if I can try and help answer some questions if people have any questions. Okay, I'm seeing so that there are some questions here, so just give me a moment. Okay, great. So the first question I'm seeing from Benoit, and he or she is asking about, for a SIL3 function, do you need to test that your function in 10 to the 8th different conditions and that it should never fail? Okay, so this is a great question. You're touching on a number of different topics in that, that one sentence you wrote. So the first point you're touching on is, in our SIL levels that we've defined in 61508, it's saying, if let's pretend we're higher continuous domains, and so that we'll use probability of failure per hour. So for SIL3, the failure should be less than 1 in 10 to the 8th hours. I will say the industry is not yet decided on, for machine learning models, should that failure rate, how do we calculate it, and should it get added to our SIL3 levels? I will give you my personal opinion. I think that for machine learning models, we have to do some kind of quantitative analysis, and I think it would be sensible for it to get added, let's say get added to the hardware failure rate. Now, should there be any change in the levels for the hardware failure rate if machine learning is being added? Maybe, maybe not. But I think at the end of the day, you're looking for a model that's achieving that level of safety. So if you add the failure rate of the machine learning to the failure rate of the hardware, and you're exceeding that rate, I think that's a good argument that you're not really meeting that SIL. So that was a little different than your question, but I would say that I I think it would be a good approach to calculate the machine learning failure rate, and maybe it's not exactly failure rate as the unit, but that probability of failure, and that should be meeting your SIL3 or your whatever SIL you're looking at target when added with your hardware failure rates. Then you had asked about, does that link to the number of test cases? I don't think it has to necessarily link exactly as a one-to-one for the number of test cases, because if you think about, failing 1 in 10 to the 8th hours, each test case, and I'll keep with the perception computer vision application, just kind of to illustrate, but if you think of each frame, right, each test case of the model, it could be one frame of your camera, and then you could be 30 frames per second, or 30 frames per minute, or the frame rate could change, but then also over time you probably have some techniques for aggregating detections over time, and one frame missing a detection or a prediction on one frame probably isn't equivalent to one failure per hour. So I don't think it necessarily has to be a one-to-one, the number of test cases to the, let's say, the SIL targets, but I think the concept that more data for higher SIL, I do think that that's a good concept to use. Okay, so hopefully I answered your question, Benoit. Let me see. Okay, so somebody has an interesting question. Looks like Bing, is the machine learning model deterministic for safety? Okay, that is also a very interesting question. I'll say kind of two answers. Okay, so there are some machine learning models that aren't necessarily fixed when they're out in operating in the world. It's called like continuous learning. And there can be ways to set up a machine learning model so that there can be some variation for when you put one set of inputs in, you may sample different outputs. And so for people who are familiar with machine learning, there is a concept used in training called dropout, where you'll essentially just turn off some of the weights in the model randomly at training, and this makes the models better. It sounds crazy when you say it, but that's something that we do in training. I would say for machine learning models in operation in safety tasks, we would want a fixed model. So the model weights at first are not changing once it's out in operation, and we're not using techniques that cause changes into the model prediction for the same input. So, dropout is turned off, and we're not changing the model weights. So in that sense, the machine learning models would be deterministic in that for one input, you'll always get the same output. But what I think also we kind of refer to when we're talking about this being deterministic or not is since you're using these machine learning models in these large complex operating domains, it feels like there's randomness because you don't exactly know how the model will perform in each of the different settings. So I think that they're not exactly non-deterministic, but we want to use statistical techniques to describe the overall performance, and that's also why I'm a big fan of linking the tests in some way to a context or important factors, so that when you're looking at the model performance, it's not just, let's say, an average from one test set, but you get a sense of how the performance changes throughout the space. So anyway, I hope that answers your question. Let's see. Is there any current certification for machine learning used for safety tasks, and against which standard? Okay, so that's another good question. Right now, out of the 61508 ecosystem, there's a technical report 5469. That technical report doesn't yet list requirements for certification, but it outlines a classification for machine learning models and then risk factors you should look at and some mitigation techniques. Out of the 26262 committee, there is, or not really, but ecosystem, let's say, there is ISOPAS 8800, which does have requirements for certifying machine learning models. And it also refers back to ISO 26262 for sections and requirements that, the existing 26262 requirements can be used for. Yeah, so that for the functional safety, those would be the two kind of, I think, most relevant standards. Somebody asked, are there prerequisites for the May training, like specific programming language or statistics? I would say no. The programming is going to happen in Python, which is, I think if you've had experience with machine learning, that's the most commonly used language for machine learning. But I think I know there's going to be kind of a mix of backgrounds, so we'll try and meet everybody where you are. If you have some functional safety background, that's helpful. If you have some machine learning background, that's helpful. But I think everybody will have kind of a mix. So I think, yeah, I don't think there's any specific hard and fast prerequisites. So people will have asked, so I don't believe the slides will go out, but the recording will be posted on YouTube. So you will have access to the recorded file. And yes, let me see if there's any other questions. I think Benoit also asked about the test data set must be 100% different to the learning data set. Yes, definitely that the samples used in training, can't be used in testing. I'll also say that, and probably a lot of people have seen this if you've had experience with machine learning, that even if let's say you have a data set and you split it into, the training part and the testing part. If it all comes from one collective data set, then there usually, there's some, I don't know, common assumptions, or it was the same group of people that collected and labeled the data. The test data on that data set is often going to be better than testing the model on the same type of data, but just from some other data set. Yeah, so anyway, so for applications where there's, let's say, more variability in the data, anyway, testing on quite different data, if it's applicable, can also be a really good, helpful to see how the model will generalize. Okay. Yes, I will be the instructor for the exida AI course. We're figuring out there might be another instructor too, but I will definitely be there. So if you would join, that would be so great. Somebody said, what was the full name of the paper on network generalization prediction? That is a great question. Let me pull up. I feel like I should know it off the top of my head. Okay, so if you're interested, they're all on Google Scholar, and here's my profile. And so the paper that I referenced was network generalization, this one, network generalization prediction for safety critical tasks in novel operating domains. So this should be publicly available, and no surprise, this looks at the example of pedestrian detection. And so that is, you can see that was in my head a lot describing it. So hopefully that helps. That's the name of the paper. There's a couple other papers you'll see if you want to search on Google Scholar that kind of relate to this area. What are the methods or tools you can use to build your safety case on machine learning? Yeah, that's interesting. Methods or tools. So we have our own, tools we use internally as exida for our safety case. Um, I would say use to build your safety case. I think a number of different methods can be helpful. Um, I would really, well, first of all, feel free to reach out to us. We'd love to talk with you about this if you're kind of interested. And if you email Exida about machine learning, you should get directed to me. So I should be able to get your info. And I do have everybody's email, so I can maybe send you an email too talking about this. I think there are a number of different methods that can be used well to kind of put together a convincing safety case. Um, I, for me, really the biggest and hardest question to answer is, does the model do what we need it to do, right? Because that's really what it all boils down to. And for machine learning models, it's hard to know, does the model do what you need it to do? So I think if you have some way to, document the functional requirements, there's relevant test cases, and not just like one test case, a sampling of testing throughout your intended operating domain to kind of give confidence that how well these requirements are met. I think that's really the biggest hurdle. Like what metrics? Okay, so, people are asking, what metrics do you typically use to evaluate machine learning models? So I would say I would expect that there would probably be two levels of metrics. One would be at, let's say, a per sample or a per frame evaluation. So people will use things like accuracy, uh, you know, those sorts of, let's say, common machine learning metrics. One thing I would say is, in addition to just, let's say, those standard accuracy type, recall, precision, those type of metrics, to also think about for your task, what impact does safety have? And so here I will very briefly, there's one figure in this paper that might be helpful. So this was a pedestrian task, and I should have an illustration somewhere where for this pedestrian task, we looked at, is the pedestrian in this data set had drivable area annotated. So we were able to identify the boxes in red. These are the pedestrians that are in the drivable area. It's going to be safety critical to find those people. The people on the sidewalks are farther away. Maybe we have a different metric for that. So this is just one specific example, but I would say, when you're thinking about your metrics, in addition to just, are you calculating accuracy or recall, what relevance does safety have on making sure that you're doing the function you need to do? And then from the, let's say, the per sample or per frame calculations, then there's generally going to be some higher level, more interpretable measure of performance. So then if we stick with our driving example, what's the probability that I collide with a pedestrian at a dangerous speed? Well, let's say any speed is dangerous, honestly. What's the probability, how many hours until I'm going to collide with a pedestrian? And so when you move from the frame-based, or per sample-based calculation to the higher, let's say, task level, there's usually some more, let's say, temporal filtering, or maybe there are other pieces in your system, not just the machine learning model, that can do a sanity check of, I'm pretty sure you detected a pedestrian in front of you 1 second ago. They're probably still in front of you if you haven't seen them walk out of the frame. So those types of techniques in your system then can build into that higher level metric, and then that, based on the task, would be, let's say, injuries per billion hours, or something like that. So that I'm not sure if that answers your question, but that would be some of what I would say. Um, and I think we're just coming up to the end of this session. Um, there's a couple questions in the chat I didn't get to, so I will reach out to folks. But also, I just want to say thank you so much, everybody, for your attention, for having some great questions. And anyway, I hope you had a fun time attending this webinar. All right, so with that, I think I'm going to have to close. But yes, I will follow up with any open questions afterwards. So thank you so much.